At 4:55 in the morning Eastern Time on September 15th, 2017, a room full of engineers and scientists at NASA's Jet Propulsion Laboratory in Pasadena sat frozen in front of their monitors, watching a single thin line of data slowly begin to waver. 93 million miles away, a spacecraft the size of a school bus was plunging into Saturn's atmosphere at roughly 70,000 miles per hour, and there was nothing anyone on Earth could do to stop it, slow it down, or save it, because they were the ones who had pointed it there on purpose. Every person in that room had spent years, some of them over a decade, keeping this machine alive across nearly 1 billion miles of empty space, and now they were watching it die by design, counting down the final seconds before the signal would simply stop. At 7:55 a.m. Eastern Time, it did. The line went flat. Cassini was gone, torn apart and vaporized somewhere in the thick clouds of a planet it had circled for 13 years, and the room erupted. Not in panic, but in a strange collision of applause, sobbing, and stunned silence, because the thing that had just happened was both a planned success and a genuine loss, all at once. In the minutes before that final loss of signal, flight controllers had been quietly bracing for something they'd spent years preparing for, and still couldn't fully rehearse emotionally. There was no backup plan, no fallback trajectory, no way to abort. Every possible failure mode had already been modeled, simulated, and accepted. The only real uncertainty left was how the room itself would react once the telemetry actually stopped arriving, and even people who had run this exact scenario in their heads dozens of times admitted afterward that watching it happen for real felt entirely different from anything a simulation could prepare them for. What almost nobody outside that room fully grasped that morning was that the destruction of the spacecraft was never really the point. The real story wasn't ending with that flatline signal. In many ways, it was only just beginning, and 9 years later it still hasn't stopped. To understand why NASA deliberately incinerated a fully functioning multi-billion-dollar spacecraft instead of simply letting it drift, you have to go back to why Cassini was sent to Saturn in the first place. The mission launched from Cape Canaveral on October 15, 1997, carrying with it the European-built Huygens probe, destined to eventually parachute down through the thick orange haze of Saturn's largest moon, Titan. It took nearly 7 years of looping through the inner solar system, using gravity assist from Venus, Earth, and Jupiter to build up enough speed before Cassini finally slipped into orbit around Saturn on June 30th, 2004. From that moment on, it became humanity's most detailed set of eyes on an entire planetary system, a system that turned out to be stranger, more alive, and more dangerous than almost anyone on the mission team had expected going in. Within a year, Cassini had already rewritten the textbooks once. In 2005, its instruments detected something erupting from the south pole of a small, icy moon called Enceladus, a moon barely 300 miles across that nobody had seriously expected to be geologically active at all. Plumes of water vapor and ice, laced with organic compounds, were venting directly out of cracks in the moon's frozen crust, spraying material out into space. When Cassini later flew directly through those plumes, its instruments caught the spray in the act, detecting water vapor and carbon-based organic molecules mixed straight into the mist. Follow-up gravity measurements eventually convinced the science team that this wasn't some localized patch of melted ice. It was being fed by an entire subsurface ocean, a genuine hidden sea sealed beneath miles of ice, and based on the chemistry detected in that spray, an ocean that looked, at least in principle, capable of supporting microbial life. Suddenly, a moon nobody had paid much attention to before launch had become one of the most compelling places to search for life anywhere in the solar system. Titan turned out to be just as strange in its own way. Cassini's radar confirmed that Saturn's largest moon has lakes and rivers on its surface, the only other place in the entire solar system besides Earth known to have stable liquid pooling openly under its own sky. Except on Titan, that liquid isn't water. It's methane and ethane, cycling through an atmosphere thick enough and cold enough to support clouds, rainfall, and standing lakes in a genuine alien version of Earth's own water cycle. Two worlds, an ice moon with a hidden ocean and a haze-choked moon with methane lakes, both discovered essentially by accident during a mission that was originally sold to the public mostly as a chance to study Saturn's rings up close. Titan had already delivered one of Cassini's most dramatic early moments before any of that. In January 2005, just months after arriving in the Saturn system, Cassini released the European Space Agency's Huygens probe toward Titan's surface, sending it plunging through the moon's thick, hazy atmosphere on a parachute descent that took roughly 2.5 hours. It became the first spacecraft ever to land on a moon in the outer solar system, touching down on a frigid, fog-shrouded plain littered with smooth, rounded stones that looked eerily like riverbed pebbles, evidence that liquid had once flowed across that exact patch of ground. Huygens only survived on the surface for about 90 minutes before its batteries gave out, But those 90 minutes handed scientists their first ground-level photographs of another world in the outer solar system and set the stage for everything Cassini would later confirm from orbit about Titan's strange methane weather. By 2017, though, Cassini was running out of fuel, and that created a genuinely difficult problem for mission planners. A dead, uncontrolled spacecraft doesn't just vanish. It keeps drifting, and eventually, gravity would pull it into something. If that something turned out to be Enceladus or Titan, both now considered live candidates for hosting biology of their own, the spacecraft could contaminate them with hardy microbial hitchhikers that had survived the trip from Earth, microbes that any future mission searching those moons for life would then have no way of telling apart from the real thing. So NASA's engineers made a deliberate choice. Rather than risk poisoning the very worlds Cassini had helped identify as promising, they decided to destroy the spacecraft completely, steering it directly into Saturn itself, where it would burn up so thoroughly that nothing would survive. They called it the grand finale, and it turned out to be one of the riskiest maneuvers ever attempted in the history of planetary exploration. Starting in late April of 2017, Cassini began flying 22 increasingly tight orbits, threading a gap roughly 1,500 miles wide between Saturn's cloud tops and the innermost edge of its rings. Nothing had ever flown through that space before, and nobody could say with certainty what was actually in it. Engineers genuinely feared it might be littered with icy ring particles, fragments too small and too faint to be spotted by any telescope on Earth, but still more than capable of punching straight through the spacecraft's hull at the tens of thousands of miles per hour Cassini would be traveling relative to that debris. Years of modeling and simulation went into the decision before anyone at JPL was willing to formally commit to it. And even then, the first dive through that gap in April 2017 was, in a very real sense, a gamble the entire team had to be prepared to lose. As an extra layer of protection, engineers positioned Cassini's own large dish antenna forward during the riskiest moments of each pass, using it almost like an improvised shield to absorb any impacts before they could reach the spacecraft's more delicate instruments. That decision meant that during the most dangerous seconds of each orbit, Cassini would fly essentially blind, unable to point its main antenna back toward Earth, and therefore unable to transmit anything in real time, leaving mission control with no choice but to wait, sometimes for hours, before the spacecraft would reorient itself and confirm it had survived. Every single one of those waiting periods carried its own quiet, private version of the same tension the team would eventually feel in September, a rehearsal for loss that 22 times in a row ended instead in relief. It worked. Cassini's own sensors detected that the gap was remarkably clear, and all 22 planned dives proceeded without triggering the emergency shielding maneuvers engineers had prepared as a backup plan. Each pass brought the spacecraft closer to Saturn than any instrument in history had ever measured the planet from before, at times skimming within roughly 1,900 miles of the visible cloud tops, close enough to directly sample the outer fringe of Saturn's own atmosphere. Then, on September 15th, the 23rd and final dive carried Cassini straight into that atmosphere for good, this time with no plan to come back out. NASA's Deep Space Network Station in Canberra, Australia, received the spacecraft's last signal at 7:55 that morning, roughly 1 minute after Cassini had entered the atmosphere from somewhere between 100 and 190 miles above the cloud tops. Within moments, it broke apart and burned away completely, becoming, in NASA's own words at the time, officially a part of Saturn. Carolyn Porco, who led Cassini's imaging team, described the mission's final photographs as a gift to the citizens of planet Earth. Linda Spilker, the mission's project scientist, called that last batch of images the mission's scrapbook, comparing the final days of the spacecraft's life to snapping a few last photos with old friends before saying goodbye. Among those closing frames were views of the tiny moon Daphnis stirring ripples into the edge of Saturn's rings, a farewell portrait of Enceladus sinking behind the planet's curve, captured across roughly 40 minutes of continuous imaging, while Cassini sat more than 800,000 miles away and sweeping wide shots of the rings themselves. None of it was shocking in the sense of hiding some secret message or revealing anything previously unknown. It was simply beautiful, deliberate, and final, a carefully curated goodbye rather than a scientific bombshell. And NASA has kept every single one of those images publicly archived ever since, freely available in full resolution to anyone who wants to look. Here's where most people assume the story of Cassini ends. It doesn't. Because while the cameras were capturing that quiet, deliberate farewell, the spacecraft's other instruments were doing something far less photogenic and far more scientifically explosive. During those 22 grand finale orbits, Cassini was recording gravity readings, magnetic field measurements, and atmospheric composition data from a vantage point no spacecraft had ever occupied before, and none has occupied since. None of it required a camera at all, and almost none of it could be fully understood in the moment it was collected. Saturn generated more data complexity than any other planetary mission humanity has ever flown. The product of 13 years spent continuously watching not just the planet, but dozens of moons, an intricate ring system, in a magnetic environment that turned out to be more complicated than anyone modeling it from Earth-based telescopes had ever anticipated. Properly processing all of it takes specialized software, painstaking calibration, and researchers willing to spend years combing through archived signal data that most people would assume had already given up everything it had to offer. 9 years after the spacecraft burned up, scientists are still working through that trove. And they keep finding things that genuinely rewrite what textbooks say about how giant planets behave. The most recent example was published in April of 2026 in the journal Nature Communications, led by researchers including Dr. Lisha Ray and Dr. Sarah Badman at Lancaster University, alongside Dr. Chris Arridge, formerly of the same institution, working with colleagues including Andrew Coates at University College London. Their study focused on something called the magnetospheric cusp, a funnel-shaped gap in a planet's protective magnetic bubble where charged particles from the solar wind can occasionally slip through and connect directly with the planet's own magnetic field, similar in principle to the mechanism that generates Earth's own auroras near the poles. At Earth, that cusp sits in a well-mapped, well-understood position near local noon, studied for decades by dedicated satellite missions. For years, scientists largely assumed giant planets like Saturn would follow a similar pattern, just scaled up. Using Cassini data collected between 2004 and 2010, years before the grand finale even began, Ray, Badman, and Arridge's team expanded the known catalog of Saturn's cusp sightings from roughly a dozen events to 67, and found something Earth's cusp simply doesn't do. Saturn's cusp isn't centered near noon at all. It's dragged sharply toward the afternoon and dusk side of the planet, typically sitting somewhere between 1 and 3 o'clock on the planet's own local clock, and in some cases, stretching out as far as 8 o'clock in the evening. That pattern lines up strikingly well with recent observations of Jupiter's own cusp, suggesting both of the solar system's largest planets share a fundamentally different magnetospheric regime than Earth does, one driven primarily by each planet's own rapid rotation rather than by pressure from the solar wind. Saturn completes a full rotation in only about 10.5 hours, less than half of Earth's 24-hour day, and that speed appears to matter enormously. Combined with a magnetosphere thick with ionized material constantly being fed in by Enceladus's own plumes, Saturn's rapid spin effectively drags its own magnetic field around fast enough to outmuscle the incoming push of the solar wind in a way Earth's much slower rotation simply cannot manage, regardless of how strong Earth's magnetic field happens to be at any given moment. Andrew Coates, who reviewed the findings but wasn't part of the study, described the result as critical evidence for a long-held theory that had never before been confirmed with this level of direct measurement, that the rapid spin of massive planets with active moons effectively takes over from the solar wind as the dominant force shaping their magnetic environment. Dr. Ray herself put it simply, saying the result allows scientists to move forward with new and improved theories about how planetary magnetospheres interact with the solar wind, and noting that the finding highlights just how much rich science can still be done with Cassini data, more than 8 years after the mission officially ended. That distinction carries weight far beyond Saturn itself. The overwhelming majority of exoplanets discovered so far that could plausibly generate their own magnetic fields are themselves large, fast-spinning gas giants, meaning this finding directly reshapes the assumptions baked into computer models used to estimate whether a distant exoplanet's magnetic field is strong enough to shield any potential atmosphere or surface life from stellar radiation. An Earth-centered model of how magnetospheres behave, one that has anchored planetary science textbooks since the earliest satellite missions began mapping our own magnetic bubble back in the 1960s, may actually represent a special case rather than the general rule, with the more common pattern across the galaxy looking a lot more like Saturn and Jupiter than like Earth. That is not the only major discovery to come out of Cassini's archive recently either. In October of 2025, a research team that included scientist Nozer Khawaja, working with data from Cassini's Cosmic Dust Analyzer, an instrument originally built to study the composition of tiny ice and dust particles, as the spacecraft flew through Saturn's E-ring, identified organic compounds never before recognized anywhere in the Saturn system, found within the icy plumes still erupting from Enceladus's south pole. Those compounds likely originated inside Enceladus's own subsurface ocean, meaning the plumes and the fine icy ring particles they continuously feed aren't just interesting ice crystals. They're functioning as a direct, ongoing physical sample of an alien ocean, delivered conveniently into the path of a passing spacecraft, without requiring a single drill or lander to ever touch the moon's surface. Fabian Klenner, one of the researchers involved, set to begin a new position as an assistant professor at the University of California, Riverside, described it as phenomenal to still be learning directly from the Cassini mission this many years after it ended, noting that an enormous amount of collected data is still waiting to be properly examined by researchers with the right tools and enough time. This finding adds to a case that has been building steadily for 2 decades, piece by careful piece, with each discovery resting on the ones that came before it rather than arriving as an isolated surprise. First came the plumes themselves in 2005. Then came the detection of water vapor and simple organic molecules inside them during later flybys. Then gravity measurements revealed those plumes were being fed by a genuine global ocean, rather than a localized pocket of melted ice near the surface. Then researchers identified sodium salts within the E-ring particles, evidence that the ocean water was in direct, ongoing contact with a rocky seafloor, a detail that matters enormously for habitability, since rock-water interaction is exactly the kind of chemistry that generates energy sources. Life depends on here on Earth, particularly around deep ocean hydrothermal vents. This newest 2025 finding, more complex organic compounds than anything previously cataloged in the Saturn system, is simply the latest link in that same steadily lengthening chain of evidence, one that took 20 years of patient, incremental research to build, rather than arriving all at once in a single dramatic reveal. Titan, meanwhile, has become the site of a much messier, still unresolved scientific argument. For years, one of Cassini's signature legacies was strong evidence supporting a global subsurface ocean beneath Titan's icy crust, based on measurements of how the moon subtly flexes in response to Saturn's gravity, an effect called tidal deformation. Earlier analysis of that data suggested a weakly differentiated interior, with a rocky core roughly 2,000 kilometers across, surrounded by a mixed shell of ice and liquid water around 600 kilometers thick, a structure that became one of the strongest pieces of evidence for Titan being a genuine ocean world hiding beneath its hazy orange atmosphere. But newer work presented at the American Geophysical Union's 2025 conference, drawing on a fresh reanalysis of Cassini's original radio tracking data using improved processing techniques, including something researchers call phase compression, has complicated that picture considerably. This reanalysis allowed scientists, for the first time, to directly measure a specific kind of tidal energy loss inside Titan, described using a value known as the imaginary part of the tidal love number, essentially a way of quantifying how much energy gets lost to internal friction each time the moon flexes under Saturn's pull. The resulting measurements point toward unexpectedly strong tidal dissipation deep inside Titan, more energy loss than a model built around a clean, fully liquid subsurface ocean would predict, since a liquid layer tends to move relatively freely under tidal stress and generate comparatively little internal friction, while a more rigid, less uniformly liquid interior tends to generate significantly more heat as it flexes. Some researchers now interpret that as more consistent with a moon lacking a clean, fully liquid ocean than with the layered, ocean-bearing interior many scientists had converged on in the years, right after Cassini's mission ended. Nobody involved in this disagreement is suggesting the earlier interpretation was careless or wrong for its time. It reflected the best analysis possible with the tools available. What's changed is the analytical technology now available to reprocess that same raw signal at a level of precision that simply wasn't accessible when the original measurements were first published. Exactly the kind of quiet, unglamorous scientific progress that rarely makes headlines, but steadily reshapes what we actually know. Saturn's rings themselves turned out to be part of this same pattern of late-arriving discovery. Gravity measurements gathered specifically during the ultra-close grand finale orbits, when Cassini passed nearer to Saturn's cloud tops and inner rings than any spacecraft ever had, allowed scientists to weigh the rings directly for the first time, sensing their subtle gravitational tug on the spacecraft's own trajectory with far greater precision than had ever been possible from farther out. The results, published in the years following the mission's end, indicated the rings are far younger than Saturn itself, likely having formed sometime between 10 and 100 million years ago, a strikingly narrow window inside a solar system that has existed for 4.5 billion years. That estimate came from combining the newly measured total mass of the rings with models of how quickly meteoroid impacts and other debris steadily darken and pollute bright ring ice over time. A lower total mass meant there was simply less material available to absorb that contamination, meaning it had to have accumulated more recently to still look as clean and bright as Cassini observed it. In other words, for most of Saturn's 4.5 billion year history, the planet may have looked nothing like the ringed icon we recognize today. If intelligent observers had been watching Saturn from Earth throughout most of our planet's own history, they likely would have seen a plain, ringless gas giant for the overwhelming majority of that time, only gaining its signature rings sometime around the era when dinosaurs walked the Earth. None of this involves the final photographs at all, and none of it involves anything resembling a hidden message or a manufactured mystery buried inside an image file. What it actually involves is something arguably more remarkable. A mission that ended 9 years ago, continuing to produce genuinely significant, peer-reviewed, headline-worthy findings on a rolling basis. That's because the sheer volume and precision of what Cassini recorded during its final ultra-close orbits was, and still is, more than the scientific community has been able to fully process, even with nearly a decade of dedicated effort from multiple research institutions working independently on different pieces of the same enormous data set. It's also worth remembering just how unprecedented those final 22 orbits actually were, as a piece of engineering, independent of anything they later revealed scientifically. No spacecraft before or since has ever deliberately threaded the narrow space between a gas giant's cloud tops and the inner edge of its ring system, repeatedly over the course of several months, gathering measurements from a vantage point physically impossible to reach any other way without accepting a real risk of destroying the entire mission on the very first attempt. As more researchers continue working through Cassini's full archive in the years ahead, it's likely that more findings along these same lines will keep surfacing, not because anything was deliberately withheld or held back for effect, but simply because 13 years of continuous, extraordinarily detailed data collection around one of the most complex planetary systems in our solar system takes far longer than 13 years to fully understand, particularly when the most valuable portion of that data, the ultra-close grand finale measurements, only exists because the mission was willing to accept genuine risk in its final months to gather it. The spacecraft itself has been gone since 2017, reduced to its constituent atoms somewhere in Saturn's upper atmosphere. Its scientific legacy, judging by the pace of publications in just the past year alone, is nowhere close to finished, and may not be for years or even decades to come. So here's the question worth sitting with. If a mission that ended 9 years ago is still producing findings significant enough to challenge decades-old assumptions about how giant planets protect themselves from the sun, findings that only became possible this year thanks to improved analytical techniques rather than any new data collection, what else might already be sitting inside Cassini's archive, fully recorded and simply waiting for the right combination of researchers, better tools, and enough dedicated time to finally notice it? The room at JPL that watched the signal go flat in September of 2017 wasn't watching an ending. They were watching the start of a decade and counting of discoveries that nobody in that room could have fully predicted, all pulled from data the spacecraft had already sent home before it ever touched Saturn's atmosphere. Every one of those findings, the tilted magnetic cusp, the newly identified organics drifting out of Enceladus, the quiet argument still unfolding over what's really hidden beneath Titan's crust, traces back to those same final nerve-wracking passes through a 1,500-mile gap nobody had ever dared enter before. The spacecraft is gone, but the questions it left behind are still very much alive, and so is the answer to what happens next.